Hello, so in this final chapter, AS Mechanics, Year 1 Mechanics, we're going to look at something called variable acceleration. So acceleration that is constantly changing over time, right? Now, as a warning, this chapter will require you to be comfortable with differentiation and integration from pure, okay? So if you haven't looked at that already, you really should before you look at the later parts of this chapter, which will require knowledge from differentiation and integration, okay? So with that out of the way, let's set the scene. So previously, so far in mechanics, what we would have seen is some object, right, or particle, something like that. And the idea is it has some initial speed, u, right? And then finally it ends up somewhere at the end of the journey with speed v. That's my final speed, right? And all of this is over a distance, right? Or technically the displacement between the 2 points, right? The displacement, which are called s, okay, s meters. And so the displacement again, as a reminder, if I start at this point here, if I start at A, displacement tells me how far away am I from A, okay? Not necessarily the distance, right? But just how far I am away from the starting point, okay? Anyway, so that's the displacement. And then the time, again, that's all over some time, right? Time t. So the idea is to get from one point to another, A to B, right, with initial speed at A and final speed at B, over displacement over some time t. And throughout this whole journey, we've had an acceleration, right? Acceleration A, right? Now, the key thing with this is the acceleration is the same throughout the whole journey here from A to B. The acceleration is kept the same, okay, which means we could apply our Suvat formula to find a missing velocity, a missing displacement, a missing time. Okay, we can use the Suvat formula here when the acceleration is the same throughout the journey. Okay, but what we're going to be looking at is what if acceleration is not the same throughout an object's journey? What if instead we have these two different accelerations, let's say 1 meters per second, and then halfway through we get to 2. So the acceleration changes halfway through. What we'd have to do there is to apply Suvat to each half of the journey. So when the acceleration is 1, we apply Suvat. And then when the acceleration is 2, then we apply another Suvat, right? So we need to consider these journeys as 2 separate journeys, right? Because the accelerations are different. Okay, we might just have to double our workload, but we can still solve some stuff, right? Just do Suvat twice if we need to. But then what if then I say, well, let's split it even more. Let's say we start with acceleration 1. And then let's say a quarter of the way through it goes to 2, and then let's say 3/4 of the way through it's 3, and then let's say at the final quarter it's 4. So now the acceleration is changing 4 times. It goes from 1 to 2 to 3 to 4. Hopefully you can start seeing the issue here is that it's going to be a lot of different Suvats we're going to need to do. We're going to have to do like 4 this time, right? Because we basically have to consider the journey into 4 separate parts, because there are 4 different accelerations here, right? And then you can imagine what the acceleration changes even more. What if now we halve it again to get 8 different accelerations, 8 different Suvats we need to consider, 8 different journeys, right? It becomes a whole mess. And actually it's a complete mess because acceleration will change constantly, okay? Very rarely will it be the same, like every second, right? Think about even in like a car, like miles per hour, something like that. It might be a very minute change, but it's not, the speed won't be exactly like 30 miles per hour every second. It might be 30.1 or 29.9. The point is, it's not going to be perfectly, ideally, kept the same acceleration every single time throughout the journey. Acceleration will constantly be changing over time. So, which means we can't just do that and just split it up. It'd be too much work, okay? So that introduces the idea of variable acceleration. Okay, so variable acceleration is acceleration that changes over time. Or, there we are. Okay, now when acceleration is not fixed, when the acceleration is not constant, we cannot use that. Okay, so how on earth can we start working stuff out? How can we work out missing displacement, missing time, missing speed, like we've done previously? How on earth can we do that now that we can't just use that, right? Because remember, that only works when the acceleration is fixed throughout the journey. Which so that means we're going to have to just consider functions, right? So now, in this case, when we have variable acceleration, the displacement or the distance, the velocity or the speed, and the acceleration are functions of time. Are all functions of time. Okay, so functions of time f of t, right? Like f of x, but with t instead of x. So actually what we're going to start looking at in a more broader sense is when acceleration can vary constantly throughout the journey. So what we want to do is actually just say it's a function, right? Some sort of algebraic function with respect to time. Okay, so as the time varies throughout the journey, what is the acceleration, what's the speed, what's the distance the object has at that particular point in time in the journey. Okay, so let's just have a look at some examples then, what I mean by all this. Okay, so I've got this question here. So we're told a body moves in a straight line such that its displacement f meters from a point O at time t seconds is given by the function s is 2t cubed minus 3t. So now you can see the displacement f is now in terms of t, this weird function of t that we're not used to, right? This is variable motion, right? But it's variable now, it's a function of t. So that means, for example, in part A, it wants to find the displacement at time 2. So when the particle is 2 seconds into the journey, what's its displacement from the starting point O? Okay, so the idea is this. Okay, so we start at O. Then say this is t 2 seconds. What's the displacement from the starting point, right? So that's what the displacement gives me, how far am I from the starting point. Okay, so that's what we're dealing with. So the particle's here after 2 seconds. How far away is it from the starting point? Well, to work that out, it's actually not too complicated, because I just sub in t's 2, right? So if t is 2, then s is 2 lots of 2 cubed minus 3 lots of 2, which is 10, and that'd be 10 meters. So actually that's saying the displacement then after 2 seconds the object is 10 meters away from the starting point O. Okay, that's what that's saying. And so in some ways this is a bit more straightforward than previous, with how we just using functions here, have to substitute stuff in. Okay, then part B, it wants the time taken for the particle to return to O. Now again, if I use that diagram again as my starting point again is O, and so the particle is moving along backwards and forwards, right, backwards and forwards away from the starting point. So it wants the time taken when it returns to O. So let's say it goes forward, right? It goes forward and then it goes backwards and then it returns back to O. Now, we have displacement. Now, again, displacement is not distance. Displacement only tells me how far am I away from the starting point. Now, if I have returned back to my starting point O, I'm at the point, right? I'm nowhere away from O. So actually, I want to set the displacement S to 0. Okay, because if I'm back at O, so again, if I use my diagram here, I start at O. Let's say I'm over here, and then I'll return back. But actually, at this point in time, I'm back at O. There's no displacement. I'm not gone anywhere away from O. So hopefully that made sense. So the displacement is 0. And so at that point, I just sub that in. So 0 is 2t cubed minus 3t. And so at that point, I'm just solving an equation for t. So I can factorise a t out. So t lots of 2t squared minus 3 equals 0. So that means t0 or 2t squared minus 3 is 0. And so if I solve this equation here, I get t squared is 3 over 2. Therefore t, if I root that, I get root 6 over 2, or as a decimal, 1.22 seconds to 2 decimal places. And so this is my solution here, okay? Because obviously at t0, initially, it starts at the starting point, so that's kind of a given. So this must be, so 1.22 seconds must be the second time, which is the time when it comes back to O. Okay, and so there we are. Okay, we've got this question here, and so I'm told a toy train travels along a straight track, leaving the start of the track at time t0. It then returns to the start of the track. The distance, s meters from the start of the track, is modelled by the formula, right? S is, and that is an S, equals 4t squared minus t cubed. And I'm given in particular t has to be between 0 and 4. Okay, and actually it says to explain this restriction. So why is t only between these certain values? Okay, so if we split up this inequality, this is saying t has to be greater than or equal to 0, but also t has to be less than or equal to 4. Now, actually, the first one we can do right off the bat, right? Because we know time cannot be negative. T has to be greater than or equal to 0, right? So time cannot be negative. So t is greater than or equal to 0. Cool. Okay, what about this second inequality now here? So this one is a bit trickier, right? How on earth do we get to t less than or equal to 4? Well, if we look at the question, it's now talking about distance. What the S we have here now is distance, not displacement. And you need to remember that distance must be positive, okay? Because distance only tells me how many steps I've walked or how far I've walked, okay? It doesn't care about how far I've walked in relation to my starting point, okay? So for example, let's say again, if I start at my point O, right? If I walked 4 meters forward and then 4 meters backwards, back to my starting point, the displacement would be 0, right? Because displacement tells me how far I am from the starting point, okay? And if I'm back at the starting point, there's no displacement because I'm back to where I am. But the distance, clearly you can see, has to be 8 meters, okay? Because that's just physically how far I've moved, how far I've walked or whatever, okay? Distance does not care about positioning or direction. Okay, so distance is a positive quantity. So also distance cannot be negative either. So that means S, my distance, has to be greater than or equal to 0, which means if S is this expression here, so therefore 4t squared minus t cubed has to be greater than or equal to 0 as well. Okay, so really at this point we need to solve this inequality. Now, we don't know how to solve this like a quadratic inequality or whatever. It's not a quadratic, it's a cubic. So actually we need to be a bit clever with this. Hopefully you can kind of spot what we can do is sort of just maybe factorise, kind of like solving it, right? So if I factorise a t squared out, I get 4 take away t greater than or equal to 0, right? Now hopefully it's a bit clearer now how we can get t greater than or equal to 4. Now, what I'm saying is this expression, these two brackets, these two factors have to be greater than or equal to 0. So if each of my factors, so the t squared factor and the 4 minus t factor, if they multiply, they have to get me a positive number. Now, t squared is positive by default, right? T squared is greater than or equal to 0 as it's a square number, right? Now think about it. What I'm saying is essentially I've got a positive then. And I'm multiplying it by this factor here, and it has to get me a positive as well. So a positive times what has to get me a positive? Another positive, right? It cannot be a negative because a positive times a negative gets me a negative. So actually, therefore, also the other factor 4 minus t has to be greater than or equal to 0. Therefore 4 is greater than or equal to t. And then I can just switch it the other way around to get t is less than or equal to 4. And there we are. So now we've shown that as well. And so therefore overall 0 has to be less than t and less than equal to 4 there. And there we are. There's the inequality there. So again, you need to consider that things must be positive when explaining certain restrictions in values here. Okay, so time and the distance has to be both positive. Okay, and so there we are. Right. Okay, so we've got this question here. So here we're told a body moves in a straight line such that its velocity at t seconds is given by v is 2t squared minus 16t add 24, and t obviously has to be greater than or equal to 0. It's positive. So then it says for part A to find the initial velocity. Now initial velocity, again, you might be thinking suvat, right? Previously, but we don't need suvat here because initial velocity is when t is equal to 0. It's initial, right? So when t is 0, if I substitute that into v, then v is going to be 2 lots of 0 squared minus 16 lots of 0 add 24. That just gets me 24. So that's my initial velocity. Okay. Then in part B, it wants me to find the values, plural, of t when the body is instantaneously at rest. Now, when it's at rest, that means the velocity or the speed has to be set to 0, right? We saw that before. It's at rest, it has no speed. So v has to be equal to 0, okay? Now, so at that point, we'd be setting 2t squared minus 16t add 24 set to 0. Now, before we solve that quadratic, instantaneously, you'll see that throughout the chapter. That means, because what we're dealing with is a variable movement, which means it's changing constantly over time. So instantaneously means it's just changing rapidly over time. So you can think of it as going to be at rest only for a split second. Right, it's going to get to 0 speed and then it's going to go back up or go back down. So that's the idea. Things are constantly changing now. Okay, so the velocity the speed will only be set to 0. Very small period of time. So it's instantaneous. These things are happening quite quickly. Okay, because it's constantly changing now. Okay, so if I now solve this quadratic, then I can just use whatever method you like. I'm just going to state the formula very quickly. Oh, minus 4. Okay. And so if I put that in a calculator, I get T6, or T is 2. Okay, and so actually both of those values make sense. And so yes, because the question says values, plural, meaning 2 or something like that. So they're both solutions here. Okay, those are the 2 times when the object is very momentarily, right, gets its speed to 0. Okay, and so those are the 2 times there. Okay, so that's saying 2 seconds in and then 6 seconds into the journey, that's when the speed is 0. Okay, then in part C, it wants the value of t when the velocity is 64. So now they told us the velocity is 64, so set v to 64, which means the that v is 64 equals 2t squared minus 16t add 24. And so again, this is just a quadratic equation. So 2t squared minus 16t. If I move the 64 to the other side, subtract by it, so that'd be minus 40 is equal to 0. And then I just solve this quadratic. Solving this, I get t is 10, or t is negative 2. But of course, as we just discussed, t cannot be negative because it's time. So we cannot take this solution here. So that means t can only be 10. And there we are. Then for part D, it now wants the greatest speed of the body in the interval 0 to t to 5. Okay. Right, so firstly, if I just restate my formula here, so v is 2t squared minus, what is it, 16t at 24, and I want to find the maximum specifically between 0 and 5 for t. Okay, so there are many ways you could approach this. What I'm going to do is probably propose 2 different ways, although they're kind of the same. But what the safe way you could do it, I guess, is well, firstly spot what function do we have here in t. We have a quadratic, right? So if we want to find the maximum, so the maximum value, well, let's just sketch the graph so we can see what the values look like, right? So I should be able to sketch quadratics. So if I sketch 2t squared minus 16t at 24. Right, well, firstly, let's just draw the graph. So we're going to have t against v here, right? Now, it's going to be a positive quadratic. So it's going to have a smiley face shape. So sort of U-shape like that. And so then we need to find the roots. So actually, we did find the roots when v was 0. We found that in part B, because that's when it goes to rest, when v is 0. So these are my roots, okay? That's when v is 0. So that means it's going to pass through 2 and 6 here. So my graph is going to look a bit like that, okay? There we are. So that's the whole graph. That's for all values of t, okay? Now, I only want the values between 0 and 5, right? So let's say 5 is here then. So actually, if I just cut off the parts of the graph I don't want, I'm going to end up with this. Okay, so it's strictly between 0 and 5, right? So it starts at 0, it's going to be up here somewhere on the y-axis, on the v-axis, and then it's going to come down. It's going to come down at 2, like this, and then at 5, it's just going to be somewhere there. Because we know it hits the graph at 6, right? But if I want to end it at 5 here, 5 again, it's going to be somewhere down here. That's where the curve will be. And so actually, this is the curve between 0, t, and 5. Okay, and the top curve is for all values of t. Okay, but this is the curve I want to consider. Okay, the equation, the function given, that's the graph for only those particular values of t. Okay, so I've just restricted, cut off the parts of the graph I don't want, that's outside of those values of t. So anything less than 0 and anything greater than 5, I don't care about. Okay, so hopefully you can spot then the maximum is just going to be the initial value when it's 0, right? It's going to be here. So the maximum, hopefully you can see, due to the graph, occurs when t is 0, right? So when t is 0, that means then v is going to be, I think we did that in part A, didn't we? Yeah, we set t to 0 in part A. We got 24, right? So if we sub t 0 into the velocity equation we got, v is 24. So that is my maximum speed, or the greatest speed. Okay, they're the same thing, right? So there we are. So you can do it that way. So you can just literally sketch the graph, cut off the graph to only the values you want, and then you can see it visually there. Okay, so that has to be 24 there at the maximum, the highest value there. The other way, without necessarily sketching the graph, is what you could do is instead, trying to think about how much room I've got. I'll do it down here, or again, it's between 0, t and 5, right? So what you could literally do is sub t 0 and sub t 5, right? You substitute endpoints, okay? So if we do that, then you'd get v is 24, as we know when t is 0. When t is 5, you'd get v is... So if I sub t's minus 5 into here, no, t's 5, sorry, t's 5. So 2 lots of 5 squared minus 16 lots of 5 add 24, you get minus 6. Well, obviously that's going to be lower. But I'm subbing my endpoints, and then I also want to consider any turning points, because remember the turning points, if you looked at differentiation, that could contain a maximum or minimum point. So so then I'm going to say and look for turning points. So that's the idea, okay, with these questions. You want to sub in the endpoints for a certain range of values. So 0 and 5 are the endpoints, right? And then any turning points in between. So to find turning points, again, we got this quadratic for v. So v again is 2t squared. What is it? Minus 16t at 24. Well, actually, hopefully you can spot here, we don't need to find the turning point because we can see from the graph. Or you could realise it's it's going to be a positive quadratic, so it's going to have a minimum. So this will have a minimum point only, okay? Because the only turning point when it's a positive, as you can see here, it's going to be a minimum point. So actually, the turning point is the minimum, and out of these two values, that's going to be my max. Okay, so the maximum value by default is v is 24. Okay, so you could do it that way as well. Okay, so in that instance, you could just, without trying to sketch the graph per se, you could just consider the endpoints of my inequality of my values of t, and any turning points in between if they're a maximum or minimum. But here I wanted the maximum, so I ignored any minimums. Okay, and so there we are. Okay, right. So let's have a look at this question here. So here I'm told at time t0, a toy car is at a point P. It moves in a straight line from a point P, then returns to P. How many times it said P here? Its distance from P at S meters. Okay, so we've got this formula here. Okay, S is a fifth of 4t minus t squared. Okay. Right. So here it wants firstly the maximum displacement. Right. So the maximum displacement, this is the displacement, right? So again, I've got this quadratic again. I've got this quadratic. So again, it's kind of another similar sort of question to what we've just seen. But here, they haven't really given me any values of t to go between. Well, hopefully you can spot then with this is going to be a negative quadratic because it's negative t squared. It's going to be a negative quadratic. So it's going to have a frowny shape. And you can see that this will have a maximum point. So actually to find the maximum for S just means I need to find the maximum of this equation. But actually we know how to find the maximum, right? You could use differentiation, or you could just kind of go back to basics and just complete the square, right? That would give me the maximum as well. So S is a fifth of 4t minus t squared, or I'm going to say minus t squared at 4t. Switch it around, okay? And actually, then I can just leave the fifth where it is, and then complete the square inside the bracket here. So, well, actually, I should factor a negative out, right? So negative a fifth of t squared minus 4t. Then I can complete the square. So then it'd be minus a fifth of t, and then a half of minus 4 is minus 2, all squared. Minus 2 squared is 4, and there we are. And then if I expand that, I get minus a fifth of t minus 2 squared. And then minus 4 times minus a fifth is going to be plus 4 fifths. Okay? And that's my completed square form. Okay? And so from that point, I can just read off. So to find the turning point, so the maximum point is what? Well, firstly, again, with the complete square form, we need to set the bracket to 0. So t minus 2 is 0, which means t has to be 2. So that is t's 2. And then when the whole bracket is 0, this goes to 0, which means we're left with 4 fifths, right? So that's my maximum point, okay? There we are. Again, you could do that alternatively by doing differentiation, right? But you should end up with that. So the displacement is going to be 4 fifths then, right? So again, this is going to be t, that's my t value, and then this is my s value, 4 fifths. So therefore max displacement is 4 fifths. Or 0.8 meters, whatever you prefer. But there we are. Okay, then for part B, it wants the time taken for the toy car to return to P. Now, I've looked at this, I've looked at it, but I think, again, there's an error with the textbook. I think it's displacement here, not distance. Because I don't think the question, the mark scheme they're given makes sense if it was distance, okay? So if it's displacement, we're dealing with here. So again, it starts at a point P. The idea is it moves in a straight line from point P, so it's going to move forward, right? And then it's going to come back around, and then it's going to hit back at P. So what's the time taken when it returns back to P? Now, as we discussed previously, that means the displacement S has to be equal to 0, okay? Because, again, displacement tells me how far away I am from the starting point. If I'm back at the starting point, I'm nowhere away. So it's 0. And so if I just set S to 0, so 0 is equal to a fifth of 4t minus t squared. And so therefore, I just solve this. Well, actually, that just means 4t minus t squared is 0. And so I can solve that by factorising t out. So t lots of 4 minus t equals 0. So t equals 0, or 4 minus t is 0, which means t is 4. And actually, it makes sense for that to be the solution, okay? Because t0 is initially, well, we know initially it starts at p. So that must be the second time t is 4 when it returns, okay? And there we are. Then in part C, it wants the total distance travelled. Now, this is where part A will help us. So as we discussed again, just as we've just seen here, again, P, it starts at P, it's going to go forward, then it's going to hit a maximum distance, right? A max distance. And then it's going to come back around and then back to P. Okay? As we just seen. Now, it wants the total distance travelled, okay? Well, actually, the total distance it travels from starting at P to this maximum here, and then back to then from the maximum back to P. Well, actually, it's just going to be the maximum displacement or the max distance twice, because it's going to go to the greatest distance ahead. Then it's going to match that. And then it's going to travel that same distance back. Okay. So actually, it's just going to double the displacement, the max displacement in part A. Okay, so the maximum distance. Oh no, sorry, the total distance. Sorry. So when it goes, so how far it's gone forward and how far it goes back to P. Right, it's going to be double the maximum. So how far has it gone forward? So it's got two lots of 0.8, which is 1.6 meters. Okay, and there we are. Okay. It's a bit quite tricky, that is, to visualise why that is, but that's the total distance. Then in part D, the values of T when the model's valid. So we're building on this again even more. So now, again, it starts from P, the starting point, then it moves forward and it comes back to P here, right? Now I'm told it returns to P, and then it kind of implies the model doesn't work after that, so we don't consider anything else after it returns back to P. So it does not consider going backwards or whatever. Once it returns back to P, that's it, the model's over. Okay, well, so that means it doesn't go it only goes forwards, right? It goes forwards from P, so it starts at P and then goes forward and it comes back to P. It does not go beyond P backwards, which means the displacement has to be positive, okay? You have to be forwards from P, never backwards from P. Which means then S can only be positive, okay? So S must be positive, as there's no negative displacement in the model. I'm going to say as the object or whatever it's called doesn't move or doesn't travel beyond P backwards. Okay, so it doesn't go in the backwards direction, so away from P, so it's not negative. Okay, so at that point then, very, very similar to an earlier question, we want to set S to be positive, which means that therefore a fifth of, what was it? 4t minus t squared, right? Has to be greater than or equal to 0. Now again, obviously we know a fifth has to be positive, so that means the bracket has to be positive as well. So therefore 4t minus t squared has to be positive as well, for the whole thing to be positive. And so again, if I factorise this, I get t lots of 4 minus t greater than or equal to 0. Now, t has to be greater than or equal to 0 by default, right? Because t cannot be negative, time cannot be negative. So again, I'm in this situation then where one factor t cannot be negative, so I've got a positive. And so I multiply this by the other factor 4 minus t, and then it has to get back a positive. So that means a positive times something has to give me positive. Well, it has to be another positive then, right? Which means this factor 4 minus t has to be positive as well, right? So since t is positive, that also means the other factor 4 minus t has to be positive. If I solve that, I get t greater than or equal to 4. no, sorry, 4 greater than equal to t, so that means t is less than equal to 4. Okay, and that's the inequality that will help me here. Okay, so t has to be less than 4. So the values of t are simply between 0 and 4. Okay, so t is between 0 because it's positive and less than 4, and that is my final answer. Okay, right. Then in this question here, we're told a particle P moves on the x-axis at time t seconds. The velocity is in the direction of x increasing. So I'm just giving the equation here. V is a fifth of 3t squared minus 10t add 3. Okay, that's the main thing really to pay attention to. Okay, then in part A, it wants to find the values of t when P is instantaneously at rest. So again, at rest means the velocity or the speed has to be equal to 0. So V has to be 0 here then. If I set V to 0, that means a fifth of 3t squared minus 10t add 3 equals 0. If I divide by a fifth, I don't care about the factor here. So that means just 3t squared minus 10t add 3 equals 0. And so then if I solve this quadratic, I get t is 10 plus or minus the root of minus 10 squared minus 4 lots of 3 of 3 over 2 lots of 3. And so if I solve that, I get t is 3 or t is a third. And so those are my two solutions, right? They're both positive, they both make sense. So those are the values, right? The plural, the two solutions for t here. Okay. And then in part B, it wants to find the greatest speed between 0 and 3. Okay, so if I just restate down here, right, again, the function is v is a fifth of 3t squared minus 10t at 3. And it wants the max speed. That would be important. The speed between 0 and 3. Okay. Now, what we've got here, well, actually, before we talk about that, again, what we can do, instead of sketching a graph, we can just consider the endpoints, the values I'm interested in. So if I sub in t0 and then t3, those are my endpoints. Right, with t0, then v is going to be a fifth of 3 lots of 0 squared minus 10 lots of 0, add 3. That will get me 3 fifths, right, or 0.6. Okay. And then if I sub in t3 into my velocity equation here, that'd be a fifth of 3 lots of 3 squared minus 10 lots of 3, add 3. That will get me 0, right? And then I need to consider the turning points, right? So the maximum and the minimums, right? Now the turning point, again, we've got a quadratic here. So what we can do is just complete the square, right? So again, if v equals a fifth of 3t squared minus 10t add 3. So if I complete the square on this here, well, actually, to make it a bit easier, if I just expand the fifth out, right, this is going to be 3 fifths of t squared minus 10 fifths, which is 2t, add 3 fifths, okay? And so hopefully, if I do that, it makes it a bit easier to see how I'm going to complete the square. Then we're going to factor 3 fifths out of the t stuff. So 3 fifths of t squared, then that'd be minus 10. Okay, well, to work out how the t will factor, well, if I do minus 2 divided by 3 fifths, I get minus 10 over 3. There we are. Okay. Then I add the 3/5. I leave the number outside. Okay. I don't bother factorising that. Okay. And so then if I complete the square in here, I'm going to get 3/5 of t minus 10 over 6 if I half that, right? All squared. Take away, then 10 over 6 all squared is 100 over 36. And then add 3/5. Then if I simplify it up here, that go to 3/5 of, then if I expand that, t minus 10 over 6 all squared. Then minus 100 over 36 times 3/5. I get minus 5 over 3, add 3/5. And so that will get me, v is 3/5 of t minus 10 over 6 all squared. And then minus 5 over 3, add 3 over 5 is minus 16 over 15. Okay. So that's in completed square form. Quite an ugly one actually to complete the square on. But there we are. Alternatively, again, you could just differentiate from the turning point. But actually now the turning point, now we set the bracket to 0. That means t is going to be 10 over 6. And then when the bracket is set to 0, then we're just left with minus 16 over 15. And so there we are. So that's the value of t, and that's the speed, that's the velocity v. Okay. Now, so actually, this will give me my minimum, right? V is so when t is 10 over. If I do it up here, then, and then when t is what was it? 10 over 6. V was negative 16 over 15. Okay. Or as a number, that is negative 1.067 to 3 decimal places. Okay. So if I highlight it, I've got these 3 values here. So when t is 0, I got v is 0.6. When t is 3, I got 0. And when t is negative, then when t is 10 over 6, I got v is this minus 1.067. Okay, so v, sort of the values to consider for v is 0.6, 0, or minus 1.067. Now you might think from that then, well, the maximum is 0.6, right? It's the highest out of 0.6, 0, and minus 1.06, right? But it wants the maximum speed. Now speed, remember, must always be positive, which means any negative value has to be flipped to a positive, which means actually what we're considering is 0.6, 0, and positive 1.06. Now those values, the 1.07, 1.06 is the bigger out of the 3. So actually this is my maximum speed. Okay, max speed is 16 over 15, right? Or 1.067 meters per second to 3 decimal places. Okay. And so there we are. Okay, that's a very nasty question, I think. But there we are. So again, the method was to just consider substituting in the 2 endpoints between 0 and 3, and then the turning points of the value there. And then I had to flip all the negatives into a positive, because in this case, it's speed. Okay, so it has to be positive quantity. Okay, so remember, speed is the positive version of velocity. Okay, hence why I did that. Okay. So there we are. Okay, that's my max speed there. Right, okay, we're going to finish off with this. So I'm told at time t0, a particle moves in a straight horizontal line from a point O, then returns to the starting point. The distance is given by S is 3t squared minus t cubed between 0 for t and also this larger value of t. So time little t can only be has to be less than this maximum limit big T. Okay, so again, if I split this up, t is less than or equal to 0, or little t, the general value of time has to be less than or equal to the upper limit for t there. So so it says given that the model is valid when s is greater than or equal to 0. That makes sense because it's distance, right? Distance here has to be positive. We need to find the value of this t here. So if s here, the distance has to be positive, that means this 3t squared minus t cubed, which equals s, also has to be positive. So again, the same idea is we sort of factorize to consider the signs. So I can factor a t squared out to be 3 minus t. And so again, t squared has to be positive because it's a square number, but also because t is positive as it's time. So therefore, the other factor, if t squared is positive, then 3 minus t has to be positive as well. So therefore, if I solve this, I get 3 is greater than or equal to t, or t is less than or equal to 3, if I flip it, okay? Well, there we are. So therefore, big T has to be 3, right? Because if I sub t for 3 here, that matches with what I've got, okay? So there we are. So that's the value of big T there, okay? Okay, cool. So that's it for this section. So again, hopefully you just got the idea now that we can just use functions. So particularly functions and formulas involving time to find displacement or the speed or velocity or whatever, right? But there we are. I'll leave it for now. I'll see you next time.